housekeeping. Your quiz or test papers were returned, and actually some of you may have also received your extra credit sheets filed in your folders, and if that happened to you, staple it back to the test when you turn in the test corrections for those 5 points, please, because those were not accounted for. Does that make sense? Yeah, so if they were returned to your folder, please staple those to your test. If you are going to turn them in and you haven't turned them in yet, then staple them to that test redo, okay? Cool, test corrections are due next Wednesday, right? I put the instructions on the board on how to do that last time, and so looking forward to getting those. Lab. This week's lab is a continuation next week. There is no new lab next week. And so I won't have a lab quiz next week either, okay? So that's 2 weeks off, right? And that'll be helpful for midterms too, because you guys probably have some exams and papers due and those types of things. So hopefully that'll give you a little bit more time to study other things. Any other housekeeping items? Any other housekeeping items? So what chapter is assigned to read? Chapter 4, right? And so you should be finishing up the chapter 3 homework now. Try to get that done, get it completed, out of the way, and then also be working on the chapter 4 learning curves. Okay? Try to stay ahead of the lecture if you can, in terms of content. And so that when you're coming in, you're reviewing instead of learning new. Cool? All right, this is one of my favorite chapters, especially in a couple different areas. We use the quantum concepts in much of analysis and in spectral work and those types of things. And so we're going to do a brief exploration of light, and we're going to talk about it from a couple different directions. Okay, we're going to start just by looking at light itself and some basic definitions. And so light is a form of energy, right? How does light move? How does light move?
Waves.
In waves, right? So, in fact, it has a dual nature. It actually has a magnetic form and the light itself, right? The electromagnetic radiation is dual in nature, right? And so, visible light we are very familiar with. We see it with our detectors. We have detectors built into our skulls, and they're called eyeballs, and those are connected to a processor called a computer, and so we can see light, right? And in fact, we can even see colors of light. Would you guys agree with that statement? Yeah. And so, or the absence of colors. And then we can also do things like diffract light. In fact, I had a demonstration out yesterday I was doing for some kids. I should have brought that one too, because this really is kind of amazing. Maybe I'll bring that next time. And so light can be refracted or change directions, and that's something that we need to consider. We can do that with a prism, as shown here, or we can do it with diffraction gratings. That's the way the modern scientist does it. And so we have these devices. Have you ever looked at the surface of a CD and seen a rainbow? You guys remember what CDs are? Okay, so our DVDs, right? Hey, they're about to go away too, aren't they? Just to let you know that. But anyway, the surfaces of them mimic a diffraction grating. And so those grooves in there are how we do a surface for an instrument to separate light into separate components. Okay? Now, I want to talk about wavelength and frequency. Okay? And I want to relate those through a mathematical equation, which is up on the board right now. And so if I'm looking up here, then frequency times wavelength is equal to a constant. Okay? And that constant we know is the speed of light in a vacuum. Okay, you guys with me? Now, does the speed of light change slightly as it changes the medium that it's in? The answer is yes to that. So as it moves from medium to medium, then it can change, right? Now, the speed of light, the accepted value for that is 3 times 10 to the 8 meters per second, right? And so just be aware of that number. Okay, now, the wavelength we're talking about, a wave, is easier seen in my mind when you're looking at a wave. Okay, this is an example of a wave. And so if I'm going from crest to crest, or from trough to trough, or I can start at midpoint to midpoint, right? And if I measure that length, that's the wavelength. Okay? From one wave to the next wave. And so we can measure that wave very easily. Now, the frequency is how many times that wave arrives per unit time, right? And so the higher the frequency, the more times it arrives. The lower the frequency, the less times it arrives. And so you'll often hear, and we'll talk about it in here, that high frequency waves deliver more energy per unit time if they have equal amplitudes, right? And instead of getting one wave per second, I get two waves of the same size per second, the same amplitude, then I would get more energy. You guys with me? I mean, if I put 3 in that same unit of time, then I would get even more energy, and so on and so on. And so when we talk about the higher the frequency, the higher energy, we're referring to that concept. Cool? You guys with me? Now, sometimes it's easier to see waves, right? And so properties of waves in motion. And so there we go, we're waving. All right, you guys want to do it together? All right, I'll start it over here. You ready? Okay, you got to stand completely in. All right, you ready? Start over here. Go. It didn't come back? Oh, let's try this one more time. All right, let's start over here again, and then we'll go across to get practice. There we go. Better. All right. So those are waves, right? And so we're moving along, it's being pushed along. I'll get to see that in a big way. I'm going to Zeus Homecoming this weekend, right? And at some point the wave will get started and it'll go around the stadium, which is kind of cool, right? I'm just going to say it. Fun anyway. Now, if we change the wavelength, right, we can see that in the same unit time that less energy is arriving, or if I have that short wavelength, then more energy is arriving, right? And so anyway, fun? All right. So I think it's even more fun to do waves from a different picture. And this is called a Rubens tube. You guys ever heard of a Rubens tube? I am going to need a volunteer. Okay? Well, no, guys, you can't do it. I need someone who can sing with a very high pitch. Can you hold a high pitch? Actually,
How high?
It needs to be pretty high to get this demo to work well. Usually a female's voice works better. And if you think you can do it, you can come try. Okay?
I don't want to outshow her.
So what we're going to do is we're going to look at waves.
Absolutely not.
Instead of light waves, we're actually going to look at sound waves. And you can only see a piece of it right there. You guys see where it pushes out? Anybody want to try? I need somebody with higher pitch. Come on down.
I might be able to do it.
So we want to hold a standing wave. Standing wave, so just hold a constant pitch high.
Very high.
Yep. Isn't that nice? You guys see it? Can you go up? No, I can't do that. So beautiful. Anybody else want to come down and just listen to me? Or talk?
No, I don't see.
You should do all your lectures with that.
Now, it actually gets really warm down here when this thing's on. I have no idea why. So it's kind of fun though, right? Good? Are we good?
I think so.
Anybody is welcome.
Whoa, anybody can see?
Whoa!
Anybody can see? Sorry.
Oh, I think that video gives you more of a gangster rap look. Oh, yeah. Whatever, you can do both.
Okay. Does anyone have a song to recommend that I might know?
Twinkle, twinkle, little star.
Yes.
The doxology.
Hold some notes in it, right?
The doxology.
Alright, twinkle, twinkle, little star.
Turn the mic, turn the mic.
What?
Turn the mic, there you go, yeah.
Twinkle, twinkle, little star, how I wonder what you are. The highest I can.
Go up.
I don't know if it would sound good.
Go for it. So are we noticing how the wavelengths get shorter as we go higher in pitch? Isn't that fun? Okay. Go low.
Oh, I can't sing low very well. Hello, darkness, light.
Into the mic. Turn the mic over. There you go.
I've come to talk. Some vision softly creeping, left the seeds while I was sleeping, and the vision that was planted in my brain still remains within the sound of silence.
Anybody else? Are we good? All right. Room is 2. I'm gonna move it out of the way so you don't have the legs around it. Well, the piece of pipe was, I remember around $10, $15, something like that. The cart's recycled. The karaoke system underneath was, it was ready to be thrown out. The CD player didn't work on it anymore. I did have to buy the Radio Shack microphone because our other one broke. And that was about $20 if I remember right.
You sure it's gonna make one for a while?
The speaker was stolen out of an old waterproof speaker that was in the garage. And then there's a couple of plastic pipe fittings that we used to make that. Oh, and then you have to have drill press. Propane tank. To get one of those is so maybe $50 to $100. Time to get done. Fair enough? $50 to $100, somewhere there. No, $50 to $100. No. Depends on how many things you can scavenge, right? If you have to buy new, it definitely costs more. If you don't, then yeah. So you can look them up. They're on a number of YouTube pages, right? They seem to be very popular with physics professors, physicists, right? Because they like to do the wave. Yeah, brings a whole new idea. Now, so this is our first math problem related to waves, and this one says the wavelength is equal to the speed of light divided by the frequency, right? And it says actually to calculate the wavelength of light that corresponds to a frequency of 7.3 times 10 to the 14 per second, and report your answer in units of nanometers. Okay? So here you go. You guys ready? Can you do it? Can you do it without me? It's just a couple conversions. It's a calculation setup, right? We have the calculation right there. It's asking for wavelength, so it's already in the form we need, right? And so lambda is wavelength. And then the speed of light is 2.998 times 10 to the 8 meters per second, right? Then what am I going to do? That's C, I just put it in, right? Divided by 7.3 times 10 to the 14th, 1 over second, or hertz. And then I need to do a conversion, so I've got one more step in my calculation. What do I need to go to? Nanometers. What am I in right now? I'm in meters, so I need a conversion. Nanometers, right? 10 to the 9 meters is equal to 1 nanometer. You want to use that one?
Would it be negative?
Oh, yes. I did that backwards. 10 to the negative 9 meters. Oh, wait, put that on the bottom. 1 nanometer is divided by 10 to the minus 9 meters. All right, slow start today. Slow start. Yeah. That's 1 over s, seconds. 1 over seconds. Yeah, my s's and 5's look a lot alike. Okay. One of the reasons, have you guys ever noticed how every math problem, or almost every math problem I do is up here on the overheads? If you notice they're all solved up here, it's because my handwriting stinks, and I know that. And I have tried to change that, and I just can't do it and work efficiently. Okay? And so I give you the solve up here, and then show you how to solve it here. And that's why it's that way, because I acknowledge that my handwriting's not, yeah, I should have been in a position. What was I thinking? Instead of being a money doctor, I'm a poor happy doctor. MD, PhD. I can see there was a lot of like, what is he talking about? How are we doing? You guys got it? So 4.11 times 10 to the minus 7 meters, and then to do the conversion, so 10 to the 9th nanometers to 1 meter, so they did the opposite direction, but we should come up with 411 nanometers. Get all those buttons pressed correctly in your calculator?
So that's per second, right?
Huh?
That's per second, right?
No, this is actually length. So you notice how we had wave over here. So our waves, some of them got as small as from crest to crest, about like that, right? And so those wavelengths would be what? 3 inches, 4 inches, or we did it in centimeters, about 10 centimeters, right? And so if those were centimeter waves, when we get to nanometer, right, that's a lot higher frequency, right? All right. So we just calculated wavelength from frequency. Would it be just as easy to calculate the frequency from the wavelength. You just rearrange the equation, right? And yeah, and you can work around that. So there'll be times that we'll ask you to do that calculation. Okay? In fact, we're building this for a bigger picture. Okay, we're going to look at line spectra, and we're going to talk about line spectra and their relationship to electrons in valence shells. Okay, or in any shell. And we're going to talk about the amount of energy that it takes to remove an electron, and we can know that by looking at it from the perspective of putting that wavelength of energy into an atom, and the atom absorbing that and then giving us that energy back sometimes as light. And so we'll talk about that and how this is the way that we calculated the movements of electrons, the energies of orbital levels, and all those things. And it started with a scientist named Bohr. So we're building this to get bored. Okay? Too bored. All right, and then to understand more of modern quantum mechanics. Because his model only worked on one atom, the hydrogen atom. They didn't work on anything else, but it was the beginning of quantum mechanics, right? Or at least the understanding of energy levels. And so, and I look at that as the beginning place, right? So, the electromagnetic spectrum includes radio waves, microwaves, infrared, visible, ultraviolet, and gamma rays, right? All of those are electromagnetic radiation. In fact, we're looking at going from one end of the scale to the other with that list, okay? From low energy to high energy. And so all of these are different forms of light, okay? So I often kind of giggle about most people's reference point to light is only visible, right? You guys with me? And so when we talk about radio waves, do we think of radio waves as light? Do you guys? But they're really a piece of the electromagnetic spectrum, and so they're light, okay? And by that definition. And longer wavelengths are associated with lower frequencies and low energy forms of light, such as radio waves and microwaves. And shorter wavelengths are high frequency, right? And those forms are X-rays and gamma rays. And so I always, every time I read gamma rays, I can't help but go to the Hulk, right? And I loved the movie, whichever one it was, where he was genetically predisposed by his father for that to happen. All right, has anybody seen that one? Oh, you guys gotta watch more Hulk movies. So anyway, best explanation in my opinion. But anyway, how did the Hulk become the Hulk? Gamma rays, all right? Very high energy radiation causing him to mutate. Is there any reality in that? Yeah, probably. Does high energy radiation cause mutations? The answer is yes. Generally, those aren't for cool things like that. Do what? No. No, we want to keep you around, so let's not make that choice. All right, so this is the electromagnetic spectrum, and I like to think about things that long radio waves are literally miles long, okay? Radio waves are miles long, right? If we're looking up there, 10 to the third meters where we go to from radio waves to long radio waves, and we can just keep going out there, right? And those are low energy waves. Then we move all the way across over here, and we're down at gamma rays. So those are 10 to the minus 11, right, in terms of the length, or shorter. Okay? But that means that gammas are much higher in energy because their frequency at that place is somewhere between 10 to the 19th and 10 to the 20th times per second. Is that a big number? That's how many zeros? 19 zeros, right? 20 zeros? That's a big number, right? How many zeros does a million have? 6, right? And we think $1 million is a lot, right? Just kind of going there, right? To kind of get that magnitude. Yes, sir?
Is it possible for them to force those waves to be even higher frequency or shorter wavelength or even longer wavelength and even lower frequency than those?
there are techniques to frequency double, or the other direction is actually easier. To make longer things go to lower energy is always an easier thing to do. In fact, if you look at leftover energy from the Big Bang, it's in the infrared microwave area, right? And so, but the initial energy from that would have been much greater, and so it would have been on the other end of the spectrum. But yeah, so things have a tendency to go to lower through process, right? But has to do interaction and with molecules, atoms, matter of some sort, and through those matter interactions, then it changes, yeah.
So I was looking at X-rays, and I always remember they have just put on like that lead vest to do
Yeah.
those. Is there any explanation why? Like,
Absolutely, 100%, because X-rays are high enough energy to remove inner shell electrons. And so when you remove inner shell electrons, then those electrons, when they're removed, the other electrons cascade down and it breaks bonding. And so when you break bonding, if you're doing that, for example, on your cellular information, then it changes it. And so because of that, then ultimately high exposure to that can cause cells to misread information and start reproducing abnormally, and we can get maladies like cancer. And so high exposure to X-rays is detrimental in that fashion. Okay, cool? Yeah. So, yeah. In fact, we use X-rays for spectroscopy and stuff, and if you use those, then you always protect yourself from the source through shielding. So, anyway, we're looking at some of the different uses. AM waves are longer than FM, and the reason FM is normally clear and those types of things is you can get more information, right, through FM, because there's more repetitions of the wave, okay? And so then we move into cell phones, which are fun, and then into microwave ovens, all right? Police radar, satellite TV, Bluetooth, heat lamps, sun lamps, X-rays. Now where do we get gammas from? Radioactive materials.
Nuclear decay, is that what you're saying?
Yep, nuclear decay. And then from off-planet sources, such as there's good evidence that black holes, for example, the gamma can escape some of those, and there's actually some interesting configurations, and it shows beams escaping, but now you'll have to take physics courses to get more of that. So anyway, hopefully I tease someone if they want to. All right. Approximate wavelength and frequency values for different types of electromagnetic radiation. And so in my mind, I like this picture better. It gives the exact same information. You guys see it? The top is the wavelength, the bottom is the frequency on that scale up there, and it shows you each type of radiation. That's what this table is doing, but to me, the picture's better than the table. Do you guys agree? Helps you to visualize that in that fashion. Now, the visible light, we're going to do a lot with that, and we normally talk about visible light. I have a question. The wavelength that we calculated, is that value in the visible part of the spectrum? At 411 nanometers? And the answer is yes. It starts about 400 nanometers is visible, right? And that's on the high energy side. The low energy side is a little under 800 nanometers, okay? So I always like to go 400 to 800. It's really more like 380 to 790, right? Somewhere right in there. That's considered what we can see with our eyes.
So what color is that?
411, it would be in the blue-violet. Violet. We can look at that here in a minute. We'll get there. Here, we'll just go there because now we got to know. So 411 would be right here, right? And so that's definitely violet. Cool? All right. You guys, I want you to take this list and arrange it from low energy to high energy. Using figure 4.4 as a reference, arrange the following types of electromagnetic radiation in order of energy. Now what's funny, if you use the figure, guess what? You just have to write it down. It's right there, right? You good? We want you to learn those. You'll get the question without the picture on a test. You with me? Yeah, so if you can learn that order, radio, microwave, infrared, ultraviolet, X-rays, and gamma rays. Lowest radio waves, microwaves, infrared, visible, ultraviolet, X-ray, gamma. So from highest to lowest is what's given there. Sorry, I said it backwards. If you did lowest to highest, it'd be the same thing, right? If you flipped it over. Good? Light absorption and light emission, all right? Matter and energy are constantly interacting with one another. You have to realize that. Light absorption occurs when an atom absorbs a wave of light from its surroundings. When it does that, it goes up in energy. It goes from ground state to an excited state. And in reference to photons, if the photon is of the right energy, it has to be of the right energy for that to happen. But when absorption occurs, then it's of the right energy. And so when that electron moves, it's storing that energy in that electron. Okay? And so then when that energy is released, then the higher energy electron goes back down to its ground state or to a lower level excited state. And when it does, it gives off energy, okay? And that energy is given off by giving some form of light. Now, it can actually do some other things in the processes that we're talking about, and especially in molecules, and we can get intersystem crossing and all kinds of other fun stuff going on from excited state to ground state. And we can get processes called fluorescence and phosphorescence related to that, and in those emissions. And then it's actually possible to decay some of the light be heat, okay? And so it's coming off in very long wavelengths, and so it's not always exactly to get exactly back what you put in. Well, energy is conserved, but you may get it in multiple forms, okay? Does that make sense? So we would get a red shift when we fluoresce, but that excess energy left through heat or vibration, okay? And so we can always account for that energy, but it's not always what goes in is exactly what comes out in real world processes, okay? So, but in ideal situations, it is exactly that. And we're going to talk about those first. So, exact wavelengths of light are given off by an atom of a particular element when it releases energy, and those wavelengths are specific to that atom, okay? So if I have a hydrogen atom, it's going to give me a specific absorption spectrum, right? When I move to helium, it's going to have a different absorption spectrum, and so on. And the same thing when we get back to emission spectrum, then each element has its own specific emission spectrum, right? And then we can start looking at atoms tied together in molecules and the relationships there. Now, sunlight, right, contains spectral lines due to the wavelengths of light absorbed by atoms of specific elements that exist in the outer layer of the sun. So those lines are shown up here, and those spectral lines are due to the elements that are found in the sun. Does anybody know what element was discovered in the sun from these spectral lines before it was known here on Earth? Helium. And in fact, the name of the sun the name helium from the element came from the sun, right? Which its name is Helios. Okay? Yeah, I believe that's Greek, is that correct? Yeah. So from the Greek, then the element was named from that relationship. It's kind of cool, isn't it? To think that we discovered the element identified in off-planet before we did on-planet. Now we use it for birthday parties. Yeah. And to make our voice high. You guys realize that there's actually a helium shortage worldwide. It's getting more and more expensive because of the number of uses for it. And we use quite a bit of helium for multiple phases in our instruments upstairs. And so it has gotten much, much more expensive over the years since I've been working here. And so anyway, all right. How about this? Identify the colors of the visible light that have the longest wavelength. What color has the longest wavelength? Just pick that, define that for me. Red, right? And the red, orange, we're starting up there in the 700s. And which has the highest frequency? Which has the highest frequency? 800 or 400 nanometers? 400 nanometers would have the highest frequency. So what color was 400 nanometers? Violet. We looked at that a minute ago, right? You guys with me? So you can answer that. And then which one has the highest energy? Violet? Hopefully you're saying violet because it has the highest frequency. The highest frequency has the highest energy. Okay? The higher the frequency, the higher the energy. Yeah. So, longest wavelength in the visible light is red with a wavelength of about 750 nanometers. I'm going 800, huh? Maybe I dropped over into the infrared. Okay. Do what? Well, when we move past violet, right? So we go blue, violet, ultraviolet. So yeah, I mean, you're just doing that stepwise fashion. And then infrared is on the other side of the red side, right? So you have infrared, red, then on the other end, violet, ultraviolet. Cool? All right. And then the highest frequency corresponds to the shortest wavelength, and that's violet light. And then the last one is violet light also. So we have an idea what light must do. All right, photoelectric effect. The photoelectric effect is easier to see in a picture. All right, and so this is kind of what we're talking about right now. When I have photons come in, then what happens is they can bump electrons loose. And if I put a one-way valve there for electrons, we haven't talked about these types of materials yet, but ultimately we will. So if I put an NP junction there and set it up appropriately and then complete a circuit, then I can actually build a photocell, right? So to produce electricity from light to get it to flow through some object. And ultimately, if you do this in a modern way, we can make what are called solar panels, right? And we can even produce electricity through what we're describing right here, okay, with the right materials. And so that photoelectric effect. Now if we go back then, in some experiments light behaves like a wave, in other experiments it just behaves like a stream of tiny particles. When it's behaving like a stream of tiny particles, it acts like a hammer and knocks an electron off of that material. Does that make sense? Or out of that shell. And so when you shine a beam of light on a metal surface in a vacuum, electrons will be ejected, and the light must be of specific minimum energy. Shining the light of high energy does not increase the number of electrons ejected. However, the brightness of the light is proportional to that. So if I increase the intensity of light, I have more photons hitting the surface, I get what? More electrons, right? So photons are corresponding to each electron that's knocked loose. And so this phenomenon is called the photoelectric effect, and the electrons that are emitted are photoelectrons, okay? So this was studied early on, and so there's the photoelectric effect. And so anyway, Einstein won a Nobel Prize for his explanation to describe this, and what he said was that electrons, or light, excuse me, behaves as tiny individual packets of energy. Even though it's coming in as a wave, right? Then it has a dual nature, is what we often say. And so each packet of light, if it contains enough energy, knocks an electron from the metal surface, increasing the brightness, increases the number of light packets, and the results in the electrons is ejected, and then the energy of the light packet is below the minimum threshold to free an electron. No electrons are emitted. So in other words, the frequency of light is important in this, right? If it's not at high enough a frequency, it won't move that electron off of the surface. And so once you go over that frequency in terms of the amount of energy, then it will remove those, okay? And different materials have that. Anyway, so this is the dual nature of light. I went back to that. Here we go. Light can be considered both a wave and stream particle, and as we said, and duality. The particles of light are called photons, and those photons' energy can be measured by multiplying Planck's constant times the frequency. Okay? Planck's constant times the frequency. And that will give us energy in joules. Energy in joules. Now, so we saw the waves. We talked about the energy increasing with the higher frequency. Now we're actually talking specifically about how to calculate that energy, right? And so this is going to be important because we're going to use this to look at electrons on atoms. So this is just building that knowledge base and trying to tie it together. So anyway, what color is a photon that has an energy of 3.28 times 10 to the minus 19 joules? What do you need to solve that? Do what? Whatever was on the slide before this. So if we go back to this, then we've got E equals H nu, right? You guys with me? So we can get to the frequency, and then we're going to need another equation to get to the wavelength, right? So here's our wavelength equation. And then the other equation that we have is E equals H nu. So you're going to use a combination of those two equations. Hoping you can put it together before I get there. So we have this equation to get to the frequency, right? The question gave us the energy, okay? Let's go back to that. And so this is E right here. So that means if I want the frequency, if I take E and divide that by Planck's constant, then that'll give me the frequency, right? And then when I get the frequency, then I can plug it in right here and solve for the wavelength. You guys got it? So, what is our frequency equal? We got that number? 4.97 times 10 to the negative 17?
Oh, wait, no.
Is that all right?
I didn't put 34.
I have 4.95 times 10 to the 14.
4.95 times 10 to the minus 14?
Positive.
Positive 14? All right, that would be appropriate, yeah. And then 1 over seconds, or hertz. And so now when I would take that value and plug it in here, divide it into the speed of light. Why don't you guys do that one? Anybody have that number? In nanometers. In nanometers. 606 nanometers. 606 nanometers. All right, what color is that? Do we need to cheat? It is red. So if I look here, here's 600, ooh. Orange, yellow, orange. Yeah, we're working towards the red end though, aren't we? So, (606 nanometers), and y'all, so look, that it goes right back to it in that font. I can go back again. I figured out how to go in circles now. You guys already knew that, but I've learned it about myself. So anyway, so 606 corresponds to an orange color. Fun? Yeah. All right. Work function. Think right here. I'm going to stop right there because that problem is going to take a little more time than what I have. So I'm making up. I'm letting you guys out like 3 minutes early. Okay, to make up for last week when I let you out 3 minutes late. Have a great weekend.